All right, thank you so much. So, yeah, today I'd like to talk a little bit about some of the work that we've been doing in Professor Claire Clemens' lab with myself and some of my colleagues on trying to uh, get better scalability for Hamilton-Jacobi Reachability Analysis. So, I'm going to focus on three main kind of thrusts. The first is how to do system decomposition for coupled systems, coupled nonlinear general systems. The second is discussing doing model reduction for safe decision making in real time for autonomous systems. And this is using this fast track framework for fast and safe tracking. And then finally, I'll get into some of the recent work on kind of warm start reachability analysis that we've been doing. So before I go into all of this, I'm sure most of you are familiar with all the Hamilton-Jacobi reachability stuff we do in the lab, but as a very brief refresher, we have some dynamical system with control and disturbance. We have some goal that we'd like to reach and or an unsafe area. And we'd like to build up this reachable set, the set of states from which we are guaranteed to reach the goal despite the worst case disturbance within the time horizon. So to do this, we lift this up to a higher dimension and we define an implicit surface function over this that is negative inside of the goal and positive outside. And then we are trying to build up a value function here that will capture the minimum cost of trajectories of the system when they are acting optimally. So this means when the control is trying to minimize this cost and the disturbance is trying to maximize, can we capture when we will be able to enter the goal, which means when we are able to attain minimum cost or negative cost. So to do this, kind of generally for our lab is that we deal with doing dynamic programming by discretizing the entire state space and updating each point in the state space using the Hamilton-Jacobi-Isaacs PDE. So, if you fix a particular point in the state space, we look at the change in value over time backwards as we build up the dynamic programming. Now here, the Hamiltonian takes care of the minimization over the control and the maximization over disturbance, but we often care about doing this minimization over time as well. And so for that, we add in this extra minimization term that turns us into our variational inequality. So when we put this all together, this is what it looks like. Here, hopefully everybody can see the video over the Zoom. We are building up our value function backwards in time. You see the time horizon at the top. And let's say I care about a time horizon of 10 seconds here. So this is our value function. Again, it will tell us if a particular state and initial time will be able to reach negative cost over time. So since we care about where this is negative, we're going to slice this at 0, pull this over, and now this will be our reachable set. So this is the set of states from which we are guaranteed to reach the goal despite worst case disturbances. Sometimes this is called reachable tube, sometimes reachable set, depending on the nomenclature. So this is really nice, of course, because we have these safety guarantees and control policies because the gradients of the value function give us the control that we need to use in order to maintain these guarantees. We built up this toolbox called Helper OC that's just largely based as a wrapper around Ian Mitchell's level set toolbox that we hope is pretty straightforward and user-friendly to use, and we're very proud of it and used it for many different applications. But of course, it struggles with complex models and uncertain environments. On the complex model side, this is because of the curse of dimensionality. We're gridding up the state space. Every extra state adds exponentially more grid points. And so we often end up using very simplistic models of real systems that may not represent the full system dynamics when we do safety analysis over this. We also struggle with uncertain environments. In some ways, this is really nice because we can handle disturbance, but we assume that this disturbance is bounded and that we're looking at the worst that the disturbance can do within this bounded set. And if we find out that these assumptions are wrong, recomputing this from scratch can be really computationally intensive, again, because of the curse of dimensionality. We can also handle obstacles, which is pretty cool. Here I'm defining this kind of second cost function around the red obstacle that is positive, high cost inside of the obstacle and negative outside. And if I know the behavior of this obstacle ahead of time, I can actually incorporate this into the computation of my value function. You can actually see building up the value function with respect to the movement of this obstacle. And in the end, I can slice this again at 0, and I end up with my reach of guaranteed to reach my goal while not running into the obstacle in the process. However, this required knowing the obstacle's behavior ahead of time, and often we don't necessarily know what this will be. So for some of the applications I'll show, which is like navigating around humans, you can't necessarily know exactly how humans move ahead of it. So given that, let's dive into some projects that we've done. So first, on the coupled system decomposition, the motivation here is pretty straightforward. If we can decompose a high dimensional system, analyze the subsystems separately, and then put it back together, we can end up with safety guarantees on the higher dimensional system. But this is to do coupled systems. So here as kind of a toy example, let's look at this 4D Dubin's car, where the state X, the position X depends on V, the velocity, and theta, the angle. Y similarly depends on theta and V. And theta and V each depend on their inputs, the rotational velocity and the acceleration. So this is a coupled system. It's unclear how exactly we would want to decompose this. And so we asked, well, what if we just kind of brutally decompose this, just slice it down the middle, rip this apart, and now we have two 2D systems. The issue is that we are missing state information, as you can see here. We're missing V on the left side and theta on the right side. So we asked, well, what if we replace that missing information with a worst case assumption over what it might be? So we treat it as a disturbance and solve for these subsystems. Them back together by saying the value at a particular X, Y, theta, and Z is the max or worst case value between the two. If I have 4D space here, what it looks like is I need to be able to decompose my goal onto the X theta space and the Y V space. I'll then do my analysis in X theta as well as Y V, and I will lift them back up to 4D. And then I'll take the max, which is in this case the intersection between the two. So if my full reachable set looks something like this in green, I know that the gray set that I computed will be a guaranteed conservative under approximation. And the proof is fairly straightforward. It's saying we're replacing this known information about the state with an disturbance that's working against us as we try to grow this reachable set. We'll end up with this conservative under approximation. Here's what it looks like for that particular problem. So here I'm showing slices in 3D, so X theta Y and X Y V. In green, I'm showing the full formulation, and in gray, I'm showing the decoupled approximation. And we're able to get about 20% of the volume in 86 seconds here, compared to the half a day for the full formulation when we grid up the state space. So this is very nice. This is the computational time comparison with number of grid points. So on the x-axis, as we go up with number of grid points, on the y-axis, I'm showing computation time. In yellow is the form formulation. In red is the decoupled approximation, where we reconstruct afterwards. And in blue is the decoupled approximation without reconstruction, with the idea that maybe in some cases you only need to reconstruct locally around states of interest. So this technique is very nice in that it's very general. You can kind of rip apart any system as you want, but as you can imagine, this can end up with very conservative results. So even in the example I showed before, we were only able to get 20% of the volume by using this technique. So we asked, well, are there some cases in which we can do better? So for example here, what if instead of replacing this missing information with the disturbance, we instead went ahead and plugged in B here and theta here? Now we have two 3D systems, which is a bit more complicated, but we managed to get rid of this disturbance term. We're going to recombine them as before. So the value at the 4D system is the max between the value and, now it should be the two 3D systems. And what it looks like here is I'm showing the 3D slice here, X, Y, and theta. And here in the middle, I'm showing an unsafe set. I'm going to project that down onto the X theta and Y theta subspaces. And this is what it will look like when I lift it back up. And now I'm going to go ahead and propagate each of the subspaces simultaneously and pay attention to the intersection between the two. Now in blue, I'm showing the direct computation, and in the hash marks, you see the decomposed computation. So here we're actually able to get it exactly, and by going down by a dimension, in this particular case, it was 254 times faster. So the caveat here is that it's for very specific forms of systems where we can have this self-contained subsystem format, and it's for particular formulations of the problem. So the approximation technique works well in general, and this technique works well when these conditions are satisfied. Okay, so that's the system decomposition. So this was nice in that we could kind of like take systems that we couldn't do before, these kind of 10-dimensional models, and make them tractable in the order of hours, or take those kinds of 4-dimensional systems and make them tractable in the order of seconds to minutes. But we still weren't quite at the point of doing real-time decision-making while maintaining safety for these higher dimensional nonlinear systems. And that motivated the second section that I'm going to talk about, which is fast track, or fast and safe tracking. So here, the idea is that using our Hamilton-Jacobi Reachability Analysis, we can do slow and accurate planning. So if I have my system, I have some obstacles, and I have the goal, doing reachability, I can end up with the optimal control I need to apply in order to get to the goal while maintaining robustness with respect to the disturbance. On the other extreme, in robotics, we often do kind of fast but less accurate planning. So let's say abstract away our system to just a point mass and try to plan using something like A*, rapidly exploring random trees, to build up a very fast path to get to the goal. Now, this is nice in terms of computational complexity and just kind of being fast in general. But when we try to actually follow this, we may find that it's not dynamically feasible or robust to disturbances. So we could end up in a collision while we try to track this. So how do we balance the two extremes? Is there something we can do where we, plan using the very, very simple version, but with this bound around it, with an understanding that we will be able to stay within this bound? This is kind of what we want to end up getting to. So here I'm showing this coupled plane model that is tracking a lower dimensional model that's planning throughout this a priori unknown space. And it's always able to stay within this bound with respect to the planning model. Note a couple key assumptions here. We are not assuming that we know the environment ahead of time. And so we are not assuming we know what the reference trajectory will be ahead of time. The planning algorithm is planning in real time. So here I'm showing the kind of two identities of our system. I'm going to call them the tracking agent and the planning agent. And for the case of this particular talk, let's look at a particular example where here I'm going to make my tracking system model only three-dimensional because we can see in 3D. Generally, this would be a higher dimensional system. And the planning system model, I'm going to have it control its velocity directly. Now, given this setup, let's ask what will be the behavior of the two agents. Well, we know that the tracking agent will be tracking or pursuing the planning agent. And we don't know what the planning agent is going to be doing ahead of time. That's missing information because we don't know what the environment is, and we may not even know what the planning algorithm is. So again, we're going to replace that missing information with a worst case assumption. Here, the worst case assumption is that the planning agent is being as difficult as possible to track. In other words, it is actively evading the tracking agent. So we are going to call it the evader. Now, given this setup, we want to ask, what will be the largest relative distance over time between the two systems? So we want to find this bound essentially around the planning agent where we know that the tracking agent will be able to stay within this bound. So note the maximum relative distance over time here is going to be equivalent to the worst possible tracking error over time, which is equivalent to our tracking error bound. So this is what we want to compute ahead of time. So to do this, because we care about relative distance, we care about relative state. Because we care about relative state, we care about relative dynamics. So the first thing we have to do is look at the relative dynamics between these two systems. So in this particular case, we set the planning agent to the origin and look at the dynamics of the tracking agent relative to the planning agent. Here we're taking the 3D dynamics and we're subtracting out the 2D planning system dynamics. Now that we have the relative system dynamics, the next step is to define what this cost function or implicit surface function should be. Here, we're going to make our cost function distance to the origin in relative state space. Because again, the origin is where our planning agent is. So we want our cost to be relative distance to the planning agent. And for our value function, what we want to capture here are the maximum cost of optimal trajectories over time. So we want to find out the maximum cost or maximum relative distance that ever occurs between the two systems over time. So here we want to take maximum cost of our trajectories. I'll put in our trajectory notation. Where here we know that the tracking agent is going to try to minimize this cost because it's trying to reduce the relative distance. And the planning agent in the worst case is trying to do the opposite, it's trying to maximize. And so we go ahead and put that in and we have our value function that we want to compute. We use our reachability toolbox to solve it, and we end up with something like this. So this, intuitively, I didn't follow exactly what was happening in this computation, and so let's kind of back out what's going on under the hood. So here I'm showing the cost function again from the beginning, and I'm taking 3 slices of this function, red, purple, and blue, and showing what these slices look like on the right-hand side. Now you can think of these slices as candidate tracking error bounds. On the top, I'm showing what they look like in the full 3D relative state space. Note that they look like cylinders because I've only defined this cost in X and Y. I don't care about relative heading, and so it's constant throughout theta. On the bottom, I'm showing 2D slices at a theta of 0. So this is where the Dubin's car, the plane, is pointed to the right. Now, let's look at these 2D slices because 2D is easy to handle, and think about what these candidate tracking error bounds mean. Well, I know, again, that I'm at a particular theta of 0, so I'm pointed to the right. And I know that the planning agent will be at the origin in each of these cases. Now, if I start the tracking agent, let's say over here on the right-hand side, well, I know that it's going to have to leave the bound in order to come back in. So this will not be a valid initial state for it to start in order for this tracking bound to be valid. In fact, I need to kind of push it back until it just barely is able to stay within the bound. If I start, say, at the edge like this, well, this is fine as long as I can turn more sharply than the bound itself. And if I start way back here, well, that's fine. I can just enter straight into the bound. So I'd expect my set to look something like this, as a set of initial states for the system to start in such that it can stay within this candidate tracking error bound. If I look at a smaller slice, like the purple one, you can imagine I would need to push this back a little bit further, so I might end up with a set like this. And eventually, I'll come to a slice that is so small that even if I start behind at the edge here, I'll need to exit the bound in order to come back in. And so this will not be a valid error bound. Okay, given that intuition, let's go ahead and run this computation again and see if it matches. So you see that we're pulling back from the right as we expected. As this computation continues, we end up with this turquoise slice not being feasible. So here we continue running it. In this particular case, the value function actually converges. And you see that we have many different slices that we could take. So both the red and purple slice produce a potential bound that we can use, where if you start inside of the purple set, you're guaranteed to stay inside of its blue set. If you start inside the red one, similarly. And in fact, because this converged, we have an even stronger statement that we can make, which is if you start inside the purple set, you're guaranteed to stay inside of the purple set for all time. On the top, you can see what these sets look like in 3D if you kind of stack and rotate the 2D sets through theta, and they get this nice corkscrew shape. Okay, so we've computed this value function, and we got it to converge in this case. I'm happy to talk more about convergence later. And we're going to take the value of the smallest invariant level set. This is because we have many different slices we could take that all give us valid error bounds, but we tend to want to reduce error in this case. And so we're going to take the slice that produces us with the tightest error bound. And that will look like this on the right. So here's what it looks like in the full 3D relative state space. But our planning algorithm and our planning agent are only aware of a 2D space, X and Y. And so we actually have to project this down onto 2D in order to get the tracking error bound in the 2D space. So this is what it actually looks like for this example. And intuitively, what this means is that if the planning agent is at the origin, the tightest bound that you can have with respect to that is one in which the Dubin's car is doing donuts or circles around that agent. Okay, so this is the pre-computation that we did. We got our tracking system model and our planning system model. We use this to get our relative dynamics that we use to inform our tracking controller, which will give us our online control, and our tracking error bound for the online planning algorithm. So now that we've talked about the pre-computation, let's discuss what happens online. So here I have some obstacles and the goal, and these obstacles are unsensed initially. And first, we're going to figure out where we are as a high-dimensional system. And based on that, we're going to decide where we want to initiate the planning system. We're going to put this planning state into our path or trajectory planner. This could be model predictive control, rapidly exploring random trees, A*, what have you. And we're also going to input locally sensed obstacles. So we're going to take obstacles, we're going to augment them by this tracking error bound, and then we're going to put that into our path or trajectory plan. Now, based on the sensed obstacles and the planning state, this will do whatever it needs to do in order to output where it wants to go next, so the next planning state. then all we have to do for the control of a high dimensional system is look at the relative state between where we are and where that next planning state is, and use the lookup table that we've previously computed to determine what is the control we should use to chase or pursue this state. And so we apply that, and we end up trying to chase that particular state. And we may not be able to track it exactly, as you see here, but we know that the deviation will never be more than the error bound. So by augmenting the obstacles, we can continue to do this on a loop, and we may violate the augmented obstacles, but we're guaranteed to never violate the true obstacles. The important takeaway here is that we are essentially allowing people to use their very simple planning algorithms, their NPC or what have you, with two small extra steps. The first one is augmenting obstacles by this error bound, which we often do in robotics anyway. We're just asking now that you augment by this rigorously computed bound. And then we simply look at the relative state between where we are and where that plan is, and use our pre-computed control in order to chase that plan. And so it's a very lightweight wrapper that goes around these very fast and simple planning algorithms. Here's the first one that we did. Here's for simulation. So here I have this green star that's going to try to get to the goal that's on the right-hand side, and there's these unsensed obstacles in the way. And my system is this 10D near hover quadcopter model. And now, even if we knew what these obstacles were, trying to compute this using our standard techniques using HJ reachability would take longer than the universe has existed, so it's not very tractable. So instead, we'd like to plan using this 3D point model and rapidly exploring random trees, or RRT. So instead, we will pre-compute this pursuit-evasion game between the two systems on the left. Now, even doing this pre-computation can be really intractable, but by using the decomposition, we'll do the X subsystem, the Y, and the Z separately, put them together to get our 10D tracking error bound, and then project that down onto X, Y, and Z. And so that's the kind of box that you can see in X, Y, and Z. So now I'm going to go ahead and plan using RRT. The green star is the lower dimensional system. As it senses obstacles, the obstacles turn red and it replans. In blue, you see the 10D near hover quadcopter model that is simply chasing this green star, the lower dimensional system. Now you see, like right there, the planning algorithm did this sudden 180 and had unexpected behavior. But because we accounted for worst case possible planning behavior, we know that we're guaranteed to stay within this bound, even when it makes a sharp turn like that. Now, this is all happening in real time in MATLAB on my laptop. And so it's much, much more scalable than the techniques from before. Here's some examples of how we've used this technique. So here is the similar simulation, but using something that we call meta planning, in which we switch between planning models of different fidelity, with the idea that you would like to choose the fastest, cheapest planning model, but that may be associated with a larger error bound. And so you need to adaptively switch into more careful models and algorithms in order to, say, squeeze between some obstacles. Here's what it looks like in practice in the lab. So here we are having a quadcopter navigate around some static obstacles, and it automatically switches into this tighter error bound in order to squeeze between the obstacles. And then on the right-hand side, we've also applied this beyond static obstacles with some collaborations with people and human-robot interaction to do navigation around one and then multiple people doing probabilistic safety in this case. And I'm happy to talk more about those projects if there's interest afterwards. Some other ways in this has been used kind of beyond our lab and beyond the techniques that I've done. So here is a project with Professor Shankar Sastry, where his students are doing a VR setup where they kind of tell the underlying planning algorithm to go through hoops and whatnot. And they're using Fast Track as the controller for actually navigating using those plans. Here's a project with Professor Marco Pavone at Stanford University. The video just froze. Getting a little jerky. But here's the video that you saw before, where we're using sum of squares optimization as the pre-computation step to try to push past these grid-based techniques that we typically use. And then here's a project in Professor Claire Tomlin's lab in which students trained a neural network classifier over the tracking control in order, again, to push past these grid-based techniques. Okay, so those were those projects. It's also been used by Professor Sanjit Sesha to do some formal methods work on kind of higher level assumed guarantee reasoning. Professor Ram Vasudevan at Michigan doing autonomous driving. Professor Sandra Hirsch at TU Munich with the Gaussian processes work. Professor Lydia Kraki and Mark Muller interested in putting this in their open motion planning library. And Dr. Gary Hewer and his colleagues are using this code at China Lake Naval. And so this has been pretty popular and really useful, I think, because it allows us to just kind of robustify these fast and simple planning algorithms with respect to the high dimensional system by pushing this computation as much as possible to the pre-computation step. Okay, so that was fast track. And then lastly, I'd like to talk a little bit about our warm start reachability analysis work. And this is some recent work that was motivated by the idea that, you've done all this pre-computation and whatnot, that's great to hear. But if you find out that your assumptions on the system model for the tracking system or the disturbances that you've assumed in the environment are wrong, well, how do you update this analysis based on their previous computation? So, if you find out that there are changes in the autonomous system, if there are changes in the external disturbances that you're assuming, or if there are changes in the behavior of other agents, like these children who are terrorizing a mall robot, can you update your computation based on your previous solution? And so this is in particular for infinite time horizon problems. For the motivating example here, because it's a bit more theory heavy, I'm going to use a very, very simple example where here we just have this 2D system where the change in position is velocity, the change in velocity is the input, the control, and we have this unsafe set. And so what the reachability analysis will produce is something like this. So this will provide us the set of states from which we may be driven into the unsafe set despite our best case control. I'm showing this kind of 2D linear system again for intuition. This theory is much more general. Okay, so using this as our motivating example, let's think about what would happen if we wanted to update our analysis based on new information. So let's say we have some trajectory of our system that has entered the unsafe area. And so we're capturing the minimum that we achieve here, and that will tell us that we managed to get into an unsafe area. But we find out that the world is different than we expected, and instead the trajectory looks something like this. We would like to be able to contract this minimum up towards the new minimum of the trajectory. And so how can we kind of enforce this contraction over time? So, this is used a lot in reinforcement learning and approximate dynamic programming, where you introduce a discount factor to enforce contraction. This is typically used for doing a sum of discounted rewards. The tricky thing here is that in reachability, we have a minimum of reward. So we want to do a minimum discounted reward. So there's a great paper by Kenne in our lab and some others in which they took the work from reinforcement learning and applied it to adapting it to this minimum discounted reward problem, where here, we take the standard dynamic programming that we're trying to do in reachability, and we add in this discount factor. Now, the great thing about this is it essentially allows the algorithm to forget over time the minimum that it took before, and you can actually allow it to forcibly contract towards the new solution. The con is that this can lead to some issues with convergence. So it can actually really slow down the convergence, which could, in some cases, as we'll show, actually make it worse than if you started from scratch and did the reachability all over again. So let's ask what happens when we don't have a discount factor. So what is really going on under the hood? Here I'm showing that same initial example again, where now I'm going to, instead of initializing at the implicit surface function or at the cost function, I'm going to start with an overly optimistic initialization. So in teal on the right-hand side, you can see the value function that I've initialized with, which is so optimistic that it's actually assuming that there's no zero level set. So there's no unsafe area at all. But then we find out that the world is worse than we were expecting. Either the disturbance bounds are worse, the control authority is weaker than we expect, or in this particular case, the unsafe set is larger than we expected. Then what happens under the hood? Well, we know that in this particular case, this component of the minimization will be active. And so we'll have the cost function minus the value function is forced to be equal to 0. And so in the very first step of this computation, it'll actually force a minimization between the teal value function that we see here and the cost function that we see in green. And so you see that it initially takes that minimization and then it proceeds as normal using our reachability analysis. So here I'm kind of explaining the intuition, but we actually have a proof here that says that when the initialization is overly optimistic, so the value function of the warm starting solution is greater than or equal to the value function of the true solution in blue, the solution will converge exactly. Now, what happens if the reverse is true? Here we have an overly pessimistic initialization. So here in teal, you see the warm start that is assuming the world is much worse than it actually is. So here we have a very, very large unsafe set that we're assuming. And it turns out that the disturbance bounds are better than expected, the control authority is stronger than we expected, or the unsafe set is smaller than we expected, which is in this particular case. Well, then this part of the equation will become active, the Hamilton-Jacobi PDE, and we can actually see a contraction happening if this maximization term over U is able to apply a contraction based on the Hamiltonian. So in this particular case, you'll see this contraction happen until it actually reaches the true solution when it balances out. I thought this was just so beautiful. Okay, so you see that in this case, and in fact, in most of the cases we tried that I'll show you, we end up converging exactly. But our proof currently just says that when the initialization is overly conservative, so the value function of the warm starting is less than the value function of the true solution, our solution will converge conservatively. So we know that it will never become more conservative than the initialization, but it may not reach the exact solution. Now, in practice, this tends to work very well anyway. So here I'm showing an initialization that's kind of random. I'm just selecting a bunch of circles here and creating a value function based on that. And so, of course, this is kind of a ridiculous initialization. And so we wouldn't expect it to converge at all, much less converge efficiently. But when I go ahead and start this, you actually see that it does work. And for a lot of the functions we are testing out here, it just works because of that natural contraction that happens from the maximization over U in the Hamiltonian. And so you can see here that it takes more time because we initialized with something that was, much worse than the standard initialization. But in fact, it does converge in this case. So if it works so well, why don't we just use this kind of vanilla implementation of HJ reachability in all cases when we're doing warm starting? When would you ever need to do a discount? Well, there are some cases in which you need to forcibly ensure that a discounting will happen. So here's kind of a trivial example of this, where I initialize with something that is not only pessimistic, so conservative, so below 0, but also just completely flat. And so we have no gradients here, and so the Hamiltonian will be 0. So in this particular case, using the standard HJ reachability, there will be no contraction that can happen because the maximization over U of the Hamiltonian will be 0 because the Hamiltonian is 0. But if we included this discount factor here, then we are forcibly making a contraction happen, as you can see, towards 0, until we're able to actually create those gradients that we can work off of. So this is what happens in the code when we actually implement the math that you see here. So here we're discounting towards the solution, and then we have to anneal that discount factor towards 1 in order for it to eventually get to the blue function. But you can see, as I was saying before, that the discounting can be extremely slow. Here's a computation time comparison of the two. So in blue, I'm showing our standard reachability for a few different examples that we tried doing in the paper. In green, I'm showing the warm starting method. And then in gray, I'm showing the discounted method for the 2D linear model that I was showing. On the 10D side, it still hadn't converged after, I forget, it was like 3 days or something, and the deadline for the paper was coming up, so we don't have the numbers for that, but it did not converge for us. Now, you see that there's, a slight decrease in time when we use the warm starting for kind of one initialization to the next. But where this really, really helps is when you need to do warm starting continuously as you continue to learn new information about the system. So this is something that will actually be explored a little bit more in the next talk, I believe, with Solmo Bonsal. But as a bit of a teaser, I want to show you here an experiment that they did where they have this turtle bot that's exploring through a room, and they're updating the safe set that's shown in red. Now, as they learn more about the obstacles in the system, they need to update the safe set over time. If they use standard Hamilton-Jacobi Reachability Analysis, you see the timestamps on the right showing how long it will take. Using the warm starting techniques, it takes, usually even less than half the time to do the update. And they actually push this even further to do a local version of warm starting where they update within the area that has new information. And so you see that we're able to push the computation time even further down by doing this local warm starting technique. But again, those details we'll get into further in the next talk. Okay, so with that, that's actually the end of what I have. Before I stop, I want to thank the people that I've gotten to work with on all these projects. This is by no means been a single person. And in fact, a lot of these projects have been really with this team of myself and Professor Mo Chen at Simon Fraser University and Solmo Bonsal at UC Berkeley, who will be presenting next. And with that, here is my email if you have any questions, as well as our GitHub links to our repositories. And I'd be happy to take questions. Thank you so much.
So I might have a very quick question. I remember you have this kind of approximation for the reachability set or reachability tube, the fast track that you mentioned. Is there actually a possible way to have another approximation of the difference between the true solution and the solution? The approximate solution that you get. Like, is there a way that you can further approximate or refine?
Oh, I think I see what you're saying. So if you do, in order to do the fast track, if I needed to do some approximation in the decomposition, is there a way I can refine that approximation to get closer and closer to the true solution? So on the decomposition side, depending on how you decide to do it, absolutely. I showed how I kind of arbitrarily chose a way of ripping apart the system into two smaller subsystems. But you can imagine that for a high dimensional system, every way you rip this apart and solve a solution will give you a different conservative approximation. And so you can actually, take the combination of all of those in order to get the least conservative of those. So that's kind of the brute force method you could do this. But one of the directions that I'm really excited about is trying to ask, for a given system, what is the most intelligent way to decompose it so that you reduce the conservativeness in the solution. There's also, where I thought you maybe were going on this question is, we were bounding the model of the high dimensional system and the lower dimensional model. Is there any way we can bound the high dimensional system with the true system? Maybe we didn't capture everything in that model. And I think that's also a really exciting direction to ask about. And
I see.
The next speaker, Solmo Bonsal, has done some work on that, of kind of bounding the true solution with the true system with the model that you have. And so please stay tuned for him.
I see. Yeah, I was actually thinking, like, if you have the true and the approximate one, after you obtain the approximate solution, is there a way to modify the Hamiltonian to have a second level set approximation, and then you can keep
interesting. Yeah, that's a really interesting idea. I hadn't thought about that. One thing that I think would be pretty fun is, there's some interest in trying to work on this from a sampling-based approach. And so trying to scale this up beyond the grid-based methods that we normally do, and instead maybe now have a probability distribution over the tracking error bound. So instead of having kind of a finite set, having with 90% confidence, you'll be able to stay within this even tighter set. But we haven't really explored. If you have thoughts on that, kind of the brute force method that we did with this, where we were like, our solutions can sometimes be way too conservative when we do fast track, is that we do this meta planning that I very quickly alluded to in the talk, where we choose to switch between different planning algorithms or planning models of different fidelity, where, if I choose to plan with something that is a little bit higher fidelity, there's less of a model mismatch between that and the high-dimensional system, and you may have a tighter error bound associated with that. So if need be, you'd be willing to switch into that in order to kind of squeeze between obstacles or do some sort of task that you can't normally do using the really, really simplified techniques.
I see. I just saw 2 hands raised. Sorry that I missed that. Let me unmute. Yeah. Hello. Hi.
Hello.
Hi. Yeah. So I know what your questions.
Yeah, thank you for the nice talk. It was very, very helpful to understand the technique and the results. I wonder how do you manage the state constraint problem when you said, if I remember well, that you can also handle the unknown environment. So if you have a robot that is moving and is moving in an unknown environment, so all the constraints are popping up at different times. So how can you modify this method in order to handle the obstacles?
Okay, let me repeat your question back just to make sure I understand. So you're saying, what I mentioned that...
I understand how you can handle an obstacle that is known from the very beginning.
Right.
What I don't understand is how you can modify the trajectory on the spot if there is a new obstacle coming in.
I see. Okay. So there are 2 ways in which, in this talk, I mentioned trying to handle a priori unknown environments. The first was when I discussed fast track, where we were planning using that low dimensional system, and then we had the bound with respect to the high dimensional one. The reason why we're able to handle unknown environments in this particular case is that we've completely separated the safety problem from the planning problem. So we know that if we plan using a lower dimensional system around new obstacles, which something like RRT or A-star can handle very, very quickly, but we augment those obstacles by the maximum possible error that will ever occur between the planning algorithm and the high dimensional system, then the high dimensional system does not have to be aware of the obstacles at all. The only thing it's aware of is where is the planning algorithm right now and what do I need to do to try to chase that?
Okay.
Yeah, so that was how we handled... Oh, sorry, go ahead.
So the planning player, in some sense, is doing the job guiding the other player.
Exactly. That's the one that's figuring out how to move. And you may not be able to chase that plan exactly, but you know that you'll never deviate by more than this kind of buffer that we put around the obstacles. Now, the other way in which we've handled unknown environments is the technique that I alluded to at the very end as a teaser that the next speaker will talk about more, where you want to create the safe set within an environment with some known obstacles, but you're going to navigate further and you're going to discover more about the environment, more obstacles potentially, and you want to update the safe set over time. And here, he can get into more details, but my understanding of the work that they did is they started by assuming everything is an obstacle. Everything you haven't sensed yet is an obstacle. So you have some limited sensing range, and you assume that outside of that, it's all unsafe. You build up what is the safe area within the limited sensing range, and then you explore within the safe area. As you explore, you sense more about your environment, and you modify your assumptions over what is and isn't an obstacle. So you're reducing the assumptions on the obstacle around you, and you're using the warm start technique that I discussed before to update your safety analysis as you move based on the new obstacles. Again, he can get into more of the details about exactly what's happening.
Okay, I will wait for the next talk. Thank you very much.
Thank you.
And there's another question from language. Hello.
Hi, Sylvia.
Hi.
Thanks for the talk. I was wondering, for the fast track stuff, one of the features of it is that you're currently computing on the grid. So you get this solution that sort of tells you a lot of rich information based on your current high dimensional state with respect to the planned state. So the tracker state is some high dimensional state that is current with respect to the state that they're trying to track. And you need that information in order to decide what to do next, if I understand correctly. You're using that gradient information in order to figure out, given what the planned state does next, you have to somehow or other make sure that you stay inside that control invariant set around the planned state. So I'm wondering if that is that in any way amenable to these semi-Lagrangian sampling techniques where you won't have all that rich information at your fingertips? You can't just go and run a couple of relatively cheap interpolations and say, okay, here's the gradient, now I know what the co-state is, I can figure out what the optimal control is, and I can run that sort of. What I'm concerned about is the online phase of the calculation. Do you, in the end, would you, even if you use these semi-Lagrangian sampling techniques, do you still need to essentially build a table of data at the offline stage in order that you can online do the calculations that you need to follow the tracking?
Yeah, great question. So you pointed out that online we are doing this lookup control where we're looking at the relative state between the high dimensional system and the low dimensional one, and looking up what is essentially a big lookup table that tells us, what control we need to apply in order to case the lower dimensional system and stay within this bound. Now, the way that we've dealt with this is that we have, the decomposition. So we have like multiple smaller lookup tables, or we've done things like the neural network-based technique that I talked about before, where we trained a classifier over the optimal control based off of the precomputation. And this was useful, but I think that there's still a lot to be explored in terms of like how can we reduce the complexity of the pre-computed large lookup table in order to be able to do the control online. So far, with the techniques that we've done, hasn't been too bad. I think largely because we're doing this least restrictive control. So, kind of when you are well inside of this error bound, you can apply LQR or whatnot, and you really need to apply that control as you approach the boundary. But I think that there's a lot to be explored in terms of like how to actually implement this effectively online. And for people who are interested in efficient computation, I would love if there are others who are interested in exploring this.
So I guess one question I would have is if you are going to, so this lookup table naturally has some error associated with it, even in the current version that you have. And you could imagine if you were trying to do some kind of compression into a neural net or something like that,
right,
that, fingers crossed, you could bound the error of that approximation. Can you, assuming that you can a priori figure out what the error of your subsequent approximation might be, is it possible to factor that error into your pre-calculation?
I don't know. That's a great question. Yeah, I would love to talk more about that idea.
Okay, thank you very much.
Thank you.
So thanks, Maurizio and Ian for the questions. Thanks, Sylvia, for the presentation, and we can go to the breakout room.